Oh, hi, welcome. Today I want to start chapter 2 in our lecture. And I want to share my screen before we get started. I want to share my screen so that you can see what I'll be writing on my whiteboard, all right? You should be seeing my screen right now. I do have the whiteboard on the right side of the screen, and this is the lecture PowerPoints. I will have two sections, section A or part A of the lecture. Part A, we will start from slide number 1 through 29 in the lecture PowerPoint slide, and then part 2 will be from slide 29 through the end of the chapter. I would like to start by just defining the terms you see here. You should commit to your memory what atoms are, molecules, and ions. On my whiteboard, I do have here the definition of an atom. Before the part of an atom, chemists used to think of matter as continuous or discontinuous. There was two schools of thought, and Greek philosophers at that time had two schools of thought, all right? That matter was continuous or discontinuous. I do have here, I don't know if you can see piece of paper. What I mean by continuous or discontinuous is if I divide this paper into two, I have two, I can subdivide it again, I can subdivide it again. And at that time, they were asking themselves that how far can you divide matter? And those schools of thought that, matter is continuous, that there is no dead end. And then the other school of thought that there is a dead end, which we call an atom. An atom means atomos in Greek. It means atomos, right? Which mean smallest indivisible, indestructible part of matter. That's just the definition of an atom. And then on the other side, molecule, all right? When we say a molecule, this refers to group of atoms bounded together, all right? Group of atoms bounded together by chemical bond, and they represent the smallest fundamental unit of molecular compound. What do we mean by molecular compound? A molecular compound consists of two or more non-metals. We'll see later on the difference between molecular compound and ionic compound. I don't want to preempt this, but the smallest form of ionic compound is called formula unit, right? We're gonna see that later on, but the point here is I want you to understand what a molecule is. Group of atoms, and they represent the fundamental or the smallest unit of molecular compound. Molecular compound. An example is CO2, you see two nonmetals, nitrogen dioxide, all right, H2O. If you look at all these, they consist of what? Non-metals. Those are just few examples of a molecule. And then when we talk of ions, these are the smallest charged or basically charged particles. What we mean by charged particles, they have overall charge. There are three classes of ions, all right? We have cation, see that, there is the anion, right? And then there is polyatomic polyatomic ion, right? These are positively charged. They are positively charged particles. This includes things as calcium, sodium, cation, and so forth. They have the overall charge positive. Then we have here anion. All right. This is stand for anions. Anion like that. They are negatively charged, right? They are negatively charged, such as chloride ion. You see that fluoride ion and so forth. And then polyatomic ions are group of atoms. Here, these are a group of atoms with overall what? Overall charge. They have overall charge. Example includes things as sulfate. We will see later on sulfite. All right. Sulfite, ITE two negative. This is sulfate. Let me show you on examples of polyatomic ion, even though we're gonna come back again to that. Here is common polyatomic ions, cyanide, acetate ion, nitrate, nitrite, phosphate, phosphite, and so forth. You'll see in the text some. This is from a different text 3.1, but in our lab, in our text, there is a table for common polyatomic ions. So that is just few examples of polyatomic ions, so that when we say ions, you should know that we have three classes: cations, anions, polyatomic ions. I'll walk you through on how to predict ionic charges for cations, predict ionic charges for anions. But for polyatomic ions, you need to learn, you need to commit to your memory, so that your life down the line will be easy. All right. I don't want to complicate things. Please get started by reading, making your own notes on polyatomic ions. So let's get started with the section 3, 2.1 atomic theory. In chapter 2, section 2.1, remember the fundamental question at that time was, what is the smallest part of matter? And in early 1700, they had started measuring chemical reagents and reagents and product, and it turns out that there was some observation which they could not explain, and this led to the discovery or the path of an atom. Okay. At that time, there were some influential philosophers. Democritus believed that the smallest part of an atom, which you cannot get or cut, uncuttable, you cannot go beyond this, is atomos, which means smallest indivisible. Two other philosophers actually had different opinion, and these are Aristotle and Plato, that they proposed that there was a dead end, which we call the atom. In early 1800, John Dalton was an English scientist, postulated the what an atom consists. His theory was only on the observation known at that time. These were the observation, the law of constant composition, the law of conservation of mass, and the law of multiple proportion. These were the observation which they didn't know the explanation behind that. And the first law here, we'll look at each one of them, law of constant composition or definite composition, which states that chemical compounds, all right, it states that chemical compounds, law of definite composition, chemical compounds are made up of elements, all right, are made up of elements, all right, in that are present in elements that are present in a small fixed ratio, all right, small fixed ratio, constant composition. For example, here, H2O, it is fixed. It will never change the ratio of hydrogen to oxygen, or sodium chloride, it will never change what? It will never change the ratio, law of constant composition. We call this Prost law in honor of Joseph Prost, who proposed or who came up with this law. This represents fixed ratio pi mass, fixed ratio pi mass. I should have indicated that. All right. So the keyword here is the ratio of mass of hydrogen to oxygen, mass of sodium to chlorine in sodium chloride. We saw this in chapter 1. We discussed that the law of constant composition. Please go read on that again. Sometimes we call this law of definite composition, which means that the relative number of atoms of each element in a compound is the same in any sample, no matter the source, Okay. The law was discovered by Joseph Prost. He was a French chemist, and working with calcium carbonate, right? He ended up with different masses of a compound, of each element in that compound. The law was one of the laws on which Dalton's atomic theory was based. Dalton's atomic theory. Okay, when we say Dalton's atomic theory, okay, it was just the postulate we will see later on the Dalton's atomic theory when we looked at the models of an atom. Let's see, the law of mass conservation is pretty straightforward. You should know this. This is just the statement that matter cannot be what? Created or destroyed. This is just a statement of that matter cannot be created or destroyed. You cannot create or destroy law of mass conservation, which means in a chemical reaction, it's just rearrangement of atoms. You don't create new atoms, you don't destroy atoms. It's just rearrangement. Therefore, mass before and mass after should be the same. This was proposed by Antoine. Please take note of these scientists who are credited for different laws. Okay, law of definite composition, Joseph Prost. Antoine, the law of mass conservation. This is also the law by which Dalton used to propose his atomic theory. Now, the law of multiple proportion states that when two elements, all right, combine with each other to form compound, they combine with a given mass or in small whole number ratio. All right. For example, sodium or calcium or even nitrogen, dinitrogen tetroxide, okay, dinitrogen tetroxide. When they combine in small whole number ratio. Other element and the ratio that represent each element in a compound, nitrogen dioxide, the ratio. So when two or more compounds exist from the same element, they cannot have same relative atoms. Okay, they have different. Please read more on a law of multiple proportion. Let's see what Dalton proposed. Remember, those laws precede the discovery of an atom. There was an attempt by scientists to explain those three laws, that what they think, for example, in the law of mass conservation, that the mass before and the mass after are the same. Okay. Therefore, John Dalton is proposing, he didn't paint a picture of an atom, but he proposed what we call Dalton's atomic theory, which is just a postulate. He didn't perform any experiment, unlike Ernest Rutherford, which we will see later on, all right? Unlike J.J. Thomson, okay? And the quantum mechanical model of an atom where we are right now, which we will look at in chapter 6. So postulate number 1, Dalton proposed that each element is composed of extremely small particles called atoms because of those three laws. And he called this an atom. Now, the element here, recall elements on the periodic table when we say atoms of sodium, I'm gonna refer to that as an element, calcium, lithium, all are made up of atoms. Now, all atoms of a given elements are identical to one another in mass and other properties, but the atoms of one element are different from atoms of the other elements. We'll see later on, if you look at the color coding, postulate number 1 is black, postulate number 2, I've highlighted that because it is no longer valid. Why? Because of existence of isotopes. We'll see later on isotopes. These are atoms of the same element with same number of protons, but different number of neutrons, and therefore mass number will change. We have what we call isotopes, and they are atoms of the same element, but Dalton was proposing that each element have a unique or identical atoms, no longer valid. Now, atoms of an element are not changed into atoms of different. What this means is if you have carbon, for example, it will have different atoms from, let's say, nitrogen. You will never change atoms of oxygen to atoms of nitrogen and so forth. All right. Postulate number 4 here states that atoms of one element, atoms of more than one element combine to form compounds. All right. Yes. If you look at postulate number 4 here, an atom of nitrogen will combine with an atom of oxygen to form a compound nitrogen monoxide, which is pretty straightforward formation of a compound. You see that. So remember the 4 postulate for Dalton, what he proposed in terms of an atom. This is in an effort to explain the aforementioned 3 laws: law of mass conservation, the law of definite composition, right? And this is what Charles Dalton proposed. Okay. Now, the discovery of subatomic particles, it turns out that, remember postulate number 2, that it's no longer valid because of subatomic particles, which you already know. Subatomic particles, these are protons with a positive charge. All right, we call these proton. I'm using the notation people. Proton, electrons. This is for electron, and then neutrons. The superscript number sign stand for the charge they carry. These are subatomic particles. You should know their notation, what they represent. We'll see later on this. But remember, when we say subatomic particles, consists of the 3 particles: electrons, protons, and neutrons. I should say neutrons. Okay, neutrons. But prior to this, there were some studies on the radioactivity electrons and the cathode rays, which enabled the early scientists to discover the 3 subatomic particles. They are the neutrons, all right, they are in the nucleus. There is protons, neutrons, and electrons. What this means is they are located in the nucleus. The 2 here, they are located in the nucleus in part of an atom, all right? This is just a illustration on the discovery or experiment performed by J.J. Thomson in the discovery of electron. J.J. Thomson is credited with the discovery of electrons. And what he did in his experiment is that a stream of negatively charged particles were found to emanate from the cathode tube causing fluorescence in the glass tube. When high voltage was applied, or when he applied high voltage to electron on either side, there was a stream of electrons from the cathode to the anode, which were deflected when subjected to magnetic field. I won't go in details into the charge-Meyer ratio, what Milken experiment did in determining the charge mass ratio, called Millikan experiment. And basically this was to determine the charge mass ratio in what we call Milken oil experiment. The picture here represent, this is Maria Curie, who studied radioactivity. Before that, Henry Becquerel had discovered that uranium emitted some heavy radiation, and they didn't know the source of radiation in uranium atoms. Okay. Henry Becquerel, all right, had studied radioactivity by looking at the heavy radiation emitted by uranium atoms, and he proposed to Madame Curie to study the source of heavy radiation. It's just credited for studying radioactivity, but Maria Curie with her husband studied the radioactivity emitted by uranium. Their studies revealed that atoms of uranium had more subatomic particles associated with it. With that discovery of radioactivity, right, the Ernest Rutherford was an English scientist, the British manager, perform an experiment we call a cold foil experiment. And in this experiment, he discovered, remember in an, what we have looked so far is Dalton's, let's see, John Dalton's atomic theory, which is what? Which is basically, or was basically a postulate of what an atom is all about. Now, Rutherford or Ernest Rutherford use alpha particles to bombard the cold foil, and the radiation somewhat deflected, all right, while others with no charge were unaffected. We'll see later on how this revolutionized the model of an atom, Before that, J.J. Thomson, maybe this should be here. J. Model of an atom. He proposed that an atom is simply a sphere, homogeneous distribution of positive, negative, positive, negative, positive, negative, positive, negative. We call this Plum Barding model of an atom, and you should know that these represent protons and these represent electrons. Remember, they are positively charged, they are negatively charged. This was Plum-Barding model, and when you say negative electrons, positive represent the proton. J.J. Thomson proposed that this is what an atom look like. Remember, at this point, they have agreed that the smallest part of matter is an atom, and how does an atom look like? Remember the discovery of subatomic particles, protons, neutrons, and where are they located? This is what Thomson proposed, and it didn't last long, all right, before this model of an atom was modified, and the third model of an atom was proposed by Ernest, all right, Ernest Rutherford. And by performing what we call a cold foil experiment, I will post that on the module for you to look at. All right. What he did is he bombarded the nucleus of cold foil using alpha. Alpha particles, which are positively charged. These are alpha particles and they are what? Positively charged. Let's keep an eye on the positive charge. What happened here is if you have it as positive charge, then passing through the cold foil here, so this is the source of alpha particle. I want you to understand that this radiation in question here, coming through here, they are positively charged. And if positive charges are going through and hitting the nucleus, which we call the nucleus model of an atom, they are deflected because in the nucleus, we have what we call protons, which are what? Which are positively charged. This is called the nuclear model, new model of an atom. In this case, I want you to have a picture of how the model has changed from Rutherford, that we have what we call the nucleus. And in the nucleus, we have protons and neutrons. But outside, we have electrons, right? Outside the nucleus, we have electrons moving around the nucleus in a circular manner. We will see that in chapter 6 when we get to quantum mechanical model of an atom. So Rutherford modified Thomson's model of an atom from here, all right, from this model to what you see on my whiteboard. We call that a nuclear model of an atom, nuclear model of an atom. His conclusion was that some particles were deflected at a large angle. Why large angle? Because if alpha particles are, let's see, these if alpha particles are just zooming into the nucleus and they are positively charged, and we are positively charged, they will be deflected. They will be deflected because of positive charges. Nucleus, we have protons and what? And then neutron. This led to a nuclear view of the atom, nuclear view of that. Just the nuclear atom. To give you a sense of the size of an atom, it is inconceivably small. The nucleus is considerably small part of an atom. This I can compare with the, when football players are playing at the center where they place the football, we consider that as the nucleus. And then the entire stadium is comparable to the size of the nucleus. So that's just the numbers. I won't ask you about the dimension, but it's good to have an understanding of how or what the size of the nucleus with respect to the entire atom. All right. So most of this nuclear atom is just empty space. All right. Whereas the dense region here is called the nucleus with protons and neutrons, protons and the neutrons. So just make your own notes comparing the Thomson model of an atom. Know the Thomson model of an atom we call Plumb-Bardeen. This is called the nuclear model of an atom. And then we have Dalton's atomic theory. Dalton's atomic theory. So those are the three models. Not two actually are the models, and Dalton's is just the postulate of what an atom is all about. Now let's see subatomic particles, which I explained earlier on. These are the subatomic particles: protons, which are positively charged, neutrons, which are neutral, they don't have any charge, electrons, which are negatively charged. You will see throughout the course and even beyond this that protons will be represented by that. All right, I did this not too long ago, the previous section. And E for electrons, and N with the superscript nu. These are neutrons, all right? Since you neutrons, they don't have any charge. So I put a superscript no to represent no charge. Well, if you look at the masses here in AMU, these stand for atomic mass unit. When you see this 1.003 comparable with that, scientists use a convenient unit of measurement, AMU. You may relate to this 1.6 times 10 raised to negative 24 grams. If you look at how many zeros you have to write before you write 1/6, about 23 zeros, right? 23 zeros, 24 zeros. So scientists use this convenient unit of measurement, AMU, wherever they are measuring this to. So if you look at the size or the mass of an electron compared to neutrons and protons, we can say the mass of an atom is basically a combination of mass of what? Protons and neutrons. Electrons are negligible. They are negligible. So those are the three subatomic particles we will we have to learn, know their charges. And by the way, these two here, they are in the nucleus. These two are in the nucleus, protons and neutrons. Electrons are outside. Let's see, shift gears to atomic number. Atomic number. What is atomic number? Atomic number is just the position of an element on the periodic table. Maybe if I can get periodic table, let's see, even though we'll come back to that, I want to probably show you what we mean by the periodic table or atomic number. It represents just a position of an element on the periodic table. This is called atomic number. Hydrogen is 1, helium is 2, 3, 4, 5, 6, 7, all the way to 118 also element. So this represent the atomic number, represent the position of, it represent the position of what? Position of an element on the periodic table. How do we determine which element an atom is by just looking at the atomic number? And it turns out that atomic number equals to the number of protons. This is a concept you should know, number of protons. So let's say sodium is number 11, all right? Position number 11 on the periodic table, which means this has 11 protons. Phosphorus, number 15, this has 15 protons. All right. And for a neutral atoms, the number of protons is something you need to know. For a neutral atom, number of what? Protons equals to number of electrons. Number of electrons. The number of protons equals number of electrons in an atom. So number 11, sodium number 11, we can say this has 11 protons and 11 what? Electrons. 11 protons. We'll see later on the number of neutrons. So here, know how to read. You should learn how to read the periodic table. Remember the number, atomic number represent the number of protons. So let's see. When you look at the recall the periodic table, each box like that for elements such as carbon, there is a number above and then there is a number below here. It's totally different from what you see here. If you see this is superscript, this is subscript, all right? This represents the isotopic notation, whereas on the whiteboard here, this represents atomic what? Atomic number. This represent what we call atomic mass on the periodic table. Perhaps maybe if I go back to this, you will see that, oh, this one doesn't have the atomic numbers. No, atomic masses, they only have what? They only have atomic numbers, not the masses. But nevertheless, if you look at the other periodic tables, they have a number below it. This represents atomic mass and atomic number. Now, this represents what we call isotope, all right? And I defined this earlier on. Isotopes are simply atoms of the same element, all right? Represent atoms of the same element with same number of protons, but different number of what? Different number of neutrons, different number of neutrons and mass number. Maybe let me highlight here mass number and number of neutrons here. The superscript numbers, before I explain all this, let's see what this means when we say atoms of the same element. Let's see example, all right? Example is carbon 612, carbon 613, and carbon 614. These are isotopes of the same element. And you see here, this is the first isotope. We have three isotopes, carbon 14, carbon 12. Now, the superscript numbers here, these are mass number, which is different from what? It is different from the atomic mass. Here, mass number designated using letter A. A is given by number of what? Protons plus number of neutrons. This is an equation you should commit to your memory. Mass number, this number here is determined by finding the total number of protons plus the number of neutrons to get A. A is the mass number. So mass number, number of protons plus what? Plus neutron. I've used equation here. A is the mass number. This represents number of protons, number of neutrons. Now, atomic number, this is the position on the periodic table, all right? Right here, atomic number, which is the position what? On the periodic table. Periodic table. So if I know the mass number, I should be able to find the number of neutrons. And that is the exercise for, if you know this and that, you can find that. In other words, number of neutrons is given by the mass number minus number of what? Protons. So understanding how this works will help you in determining the subatomic particles. There is another way of noting down the isotopes, and I may say isotopic notation so that you know or you are well-rounded. I can have this, let's say 6 and 12, or with an even 12 like that. It's the same thing. It is understood that this is an isotope of carbon 12, position number 6. This is an isotope, always chemical symbol, even, and a number. This is understood to be the mass number. Always this is what? Mass number. This will be handy wherever you'll be asked to find what? The subatomic particles. So if I look at the chemical symbol here, don't think that it is only for what? Only for element carbon. We have chlorine 35, which can be Cl and then 35 and then 70 like that, or chlorine 37, which can be Cl and then 37 and chlorine is number 17, right? Chlorine is number 17. Where I'm getting those numbers, you see here, chlorine is number 17 on the periodic table. So atomic number, and this is the mass number right here. This is the mass number, and this is what? Atomic number, which is the position on the periodic table. So learn how to interpret or read both notation for isotopic given in this format. It's pretty straightforward. Any element is not only meant for carbon, any element on the periodic table, all right? Chlorine 37, all right, copper 65, copper 63. You should know what this means. 65 or copper 63. what those means. You'll be given, you don't have to memorize those. So we can calculate the subatomic particles. All right, we can calculate the subatomic particles for these isotopes. All right, I've divided the isotopes, atoms of the same element with different masses, because of the difference in what? Number of neutrons. Number of neutrons are different. Below are the 4 isotopes of carbon. Carbon, we call this carbon 11, carbon 12, carbon 13. They have the same number of protons because they are the same number. If you look at the number of electrons, number of neutrons. So protons plus neutrons gives you the mass number 6. I mean, 6 plus 5 is 11, 6 plus 6 is 12, 6 plus 7 is 13, and then 6 plus 8 is 14 for carbon 14. For carbon 14. So the purpose of this is just to give you an example on how to find the subatomic what? Subatomic particle, And I want to just use this slide to see if you, to show you how to determine the subatomic particles, all right? Typical question in the exam. In each of the following indicate the number of protons and the neutrons. In A here, it's assumed that at this point, you know how to name most chemical element on the periodic table and their symbol. For example, if I don't know what phosphorus is, I wouldn't be able to know which position it is on the periodic table. Phosphorus has the chemical symbol P, and this is number 15 on the periodic table. In case you're wondering, yes, I'll give you in the periodic table similar to this in the exam. All right, but if you don't know that this is phosphorus, you'll just be guessing, and you may end up, maybe thinking it is potassium for P if you don't know the chemical symbol. So I know this is phosphorus, and I can write this as P with the mass number of 32, and it is position what? Position 15. So this will have A, which is mass number, is given by the number of protons plus the number of what? Number of neutrons. So I know this is 32, 15 plus number of neutrons. Rearranging the equation, therefore number of neutrons equals to 32 minus 15, which is equals to 17 neutrons. So A here is neutron. Note that I had to rewrite this so that I can do this. 32 is because of the mass number. So next time, if you are given the chemical name or chemical symbol with an ion and a number, this is not atomic number, but mass number A. Remember the notation, mass number? And then if you look at this iodine, all right, iodine is number 53 on the periodic table. That is 53, and we have 131. So here, this is the number of protons, which is the position on the periodic table. This is A, which is what? Mass number, which is number of protons plus number of neutrons, number of protons plus number of neutrons. Therefore, we are looking at what? A equals number of protons, number of neutrons. I know this is 131 equals to 53 plus number of neutrons. Therefore, number of neutrons, 131 minus 53, which is equals to 78. Please check that, 78. So that's how you you determine the number of neutrons. If it was for electrons, number of electrons here is equals to number of electrons, the same thing. If I go here, number of electrons equals to 15, it's the same thing, 15, 15. In the fallout here, it's the same thing. You are expected to know the chemical symbol. This is argon, which is what? Argon, which is 18, and this is 40. The number of neutrons is 40 minus 18, which is the same as 22. Number of electrons is 18. Number of protons is 18. This is for argon. You need to know how to read the periodic table. This is argon number 18. That's how I got this number position on the periodic table. For zinc, all right, zinc, this is number 30 on the periodic table. This is 65, which means number of protons 30, number of electrons is 30, number of neutrons is 65 minus 30, which is 35. 35. So that's how you determine the what? The subatomic particles, determination of subatomic particles using the equation. You need to remember this equation. A mass number equals to number of protons plus number of neutrons. This is take home message. And then for a neutral atom, number of electrons equals to number of protons. This will help you in determination of subatomic particles. All right, let's shift gears to section 2.4, atomic mass unit, which I explained earlier on. It's a unit used by chemists to express the masses of subatomic particles, which they are very extremely small masses. The heaviest known is 4 times 10 to negative 22 grams. You look at that as a small number. So we use a scale at an atomic level. We call AMU. Sometimes we use just this for AMU, but I think it is better to use atomic mass unit. This is, you can relate the AMU with the grams, 1.66 times 10 to negative 24, 1.66055 times 10 to negative 24. Gram is something so small that it's hard to work with, so we use AMU. Now, let's see, atomic weight on the periodic table, all right? Having gone through the subatomic particles, atomic weight, all right, atomic weight is given by summation of isotopic mass in AMU, in atomic mass unit, times, this is times isotopic abundance in the abundance, like that. This is the equation used to determine the atomic weight in AMU. Remember, this is in AMU here. This means If we know all naturally occurring isotopes for an element, we can calculate its atomic weight. For example, silicon, all right? For example, silicon has 10 isotopes. Find the atomic mass of silicon. We just use this equation. Let's see, this is just the equation I have here. Sigma here means summation. Isotope mass or isotopic mass in AMU, you will be given that fractional neutral. Fractional, what does that mean? If you are given, let's say 98% abundance, fractional is 98 over 100, which is 0.98. You're gonna use this in that equation. You will use that in that equation. For all natural isotopes, the way this is for all natural isotopes. Perhaps maybe solving an example will help you understand the concept of calculating the atomic weight of an element, atomic weight of an element. For example, here learning on the learning check, only 2 isotopes of copper occurs naturally. Remember, Cu, this is chemical symbol for copper, hyphen 63, this is mass number, an isotope of mass number 63, with each mass unit 62.9296 AMU, and the abundance in agent 72.15, and copper 65 with its mass, atomic mass in AMU 64.9278. All right, and its abundance is 30.38. Calculate atomic mass or atomic weight. That's the average masses of copper. With this, you see atomic weight is given by the summation of isotopic mass, and remember in AMU times isotopic what? Isotopic abundance. Fractional, it's got to be in fraction. So with that, it's just isotopic mass for the first isotope. In AMU, this is 62.9296 times 0.7215. I'm changing that into fraction. Do not use percent as in 72.15. And then times here, second isotope is 64.9278 times fractional 0.3083. Crunching them, plugging in your calculator, you should get 65.42 AMU. Remember, this numerical value may look exactly the same as the one on the periodic table. Let's relate that. Maybe I can pull a periodic table with the atomic masses. All right. Let's see, this one has atomic masses. Yeah, this one has atomic masses. If you look at copper, for example, right here, maybe going up. I shall have it periodic table. I wanted to pull one with the atomic masses so that you see. I think this is clear. Yeah, copper is 65. This is where we are, 65.55, 65.55, of which, all right, we have here, it was just an approximation because of the isotopes there. When we say molar mass, right, that means it 1 mole. So if we are, when we say molar mass, so that you get it for copper, 65.42 grams per mole. What that means, 1 mole so if we have Avogadro number of atoms of copper here, Avogadro number of copper atoms, then it's gonna weigh this. But if we have only one, and then it will weigh this in AMU, of which if we change to grams, it is relatively small number, relatively small number. Nevertheless, please practice on how to calculate the atomic weight given the percent abundance. One thing you need to remember is always the percent abundance add up to 100. So if I have 4 isotopes and I'm given percent for 3, and then I'll just have to do the mass, subtract from 100. If I have 2 isotopes and I'm given only percent for 1, I subtract from 100% to get the percent abundance for the other one, and then proceed with the calculation of atomic weight. Now, sometimes we use machines to determine the atomic weight of isotopes. For example, here is determination of atomic mass of chlorine 35 and chlorine 37. See that. Perhaps in the future, you will get to use the instruments such as matrix assisted laser disruption time of flight to determine a special technique for determining the mass of atoms. Other than that, I just want to end this first session, and we'll come back again for the part B of chapter 2. Thank you.